The protein that forms the structure of all living organisms is itself a polymer. And, besides that, carbohydrates, the main source of energy for living organisms, are also polymers.
Oh yeah, I totally forgot about that.
And not just that, almost everything that we use in our daily lives, such as fabrics, bags, bottles, modern utensils, parts of computers and mobile phones, face masks, along with parachutes and bulletproof materials, are all made up of polymers.
Hang on. Did you just say bulletproof materials?
Yup, a special form of a polymer called Kevlar is used to make bulletproof vests and other necessary objects used by the military.
Wow, I never knew that Kevlar is a polymer too.
Well, now you do. Anyway, you may have heard about PET and nylon a lot, since they're the most widely used polymers in the world.
Absolutely. I know that PET is most commonly used for packaging foods and beverages, especially soft drinks, juice, and water. Nylon, on the other hand, is used in clothing, as reinforcement in rubber materials like car tires, and as a rope or thread.
Great. And since we've already discussed polymers in the previous level, what else do you remember about it?
If I recall correctly, polymers are long-chain molecules formed by joining smaller molecules.
Good. And do you know what the process is called?
Oh, yeah. I remember the process through which polymers are formed by joining smaller molecules is called polymerization. The smaller molecules that join together to form a long chain are called monomers, while the long chain molecule that's formed is called a polymer.
That's right, Divash. I'm impressed. You remember all of that.
Thanks. So, teacher, what's new about polymers for today's lesson?
Well, let's start with this. Generally, polymers are macromolecules made up of many repeating units. Based on their structures, polymers could be a straight chain or linear, branched, or cross-linked.
Okay, and teacher, if I remember right, polymers also be classified on the basis of their source of origin, as natural and synthetic, or organic and inorganic, right?
Absolutely. Proteins, carbohydrates, and DNA are examples of natural or organic polymers.
And as we've already discussed earlier, polyethylene and nylon are some examples of synthetic polymers.
Correct. Other than that, polymers are also classified based on properties like elasticity, moldability, thermal stability, among others, into groups like elastomers, fibers, thermoplastics, and thermosetting plastics. For instance, polysiloxanes are used to make electrical insulation and protective coatings.
Wow. So there are a lot of ways in which the polymers can be classified.
Exactly. And to add to that, we can also classify polymers into two types based on their formation process.
Oh, I know about that. The polymers formed by addition polymerization are called addition polymers, while those formed by condensation polymerization are called condensation polymers.
Bingo! If you know all of that, then you may also remember about their polymerization reactions as well.
Although we've learned about addition polymerization in the AS level, I think I'll need a refresher for condensation.
Okay, then let's cover condensation polymerization today.
Awesome.
But before that, can you tell me how addition polymerization works?
If I recall correctly, addition polymerization simply links smaller molecules called monomers without the generation of byproducts.
Indeed.
So how is condensation polymerization different from that?
Well, condensation polymerization is a process in which monomers are joined together and condensed to form long-chain polymers. In this process, smaller molecules are eliminated.
Hang on. If monomers are joined and condensed, then what sort of compounds are eliminated during the condensation process?
Usually, small molecules like water, hydrogen chloride, and ammonia are eliminated. The kind of byproduct produced depends on the two functional groups which interact.
I see. And teacher, what sort of compounds usually undergo condensation polymerization?
Well, bifunctional monomers are essential for condensation polymerization.
Bifunctional monomers. What are those?
They are compounds which possess two functional groups in the same molecule. These functional groups may be identical or different to each other.
Compounds with two functional groups. So if two OH groups are attached to a hydrocarbon, can it be an example of bifunctional monomer?
Of course, and apart from diols, other examples of bifunctional monomers include diamine, dicarboxylic acids, hydroxycarboxylic acid, aminocarboxylic acid, and dioyl chloride.
Understood. And if I'm not wrong, bifunctionality ensures the expansion of the chain through either of its sides.
Indeed. Now please take note that a compound containing two different reactive functional groups in the same molecule can undergo self-condensation to form a condensation polymer.
Oh, wait. So what you're saying is only a kind of monomer with two different reactive functional groups will be able to form a polymer, right?
Absolutely. Now, in general, there are two types of condensation polymers, polyesters and polyamides.
I'm familiar with both of them.
Then, do you want to explain what they are, starting with polyester?
Sure. Polyesters are a kind of condensation polymer that have a large number of ester groups as a connecting link. The general structure of a polyester looks like this. Here, the COO group is called an ester functional group, and since it links two different groups or monomers, it is also known as an ester linkage or ester bond. And because so many ester linkages are present in its polymers, they're called polyester.
Nicely explained. Moving on, let's talk about how polyesters are made. They're usually made through the condensation polymerization reaction between diol and dicarboxylic acid.
And what are those things?
Generally, organic compounds with two hydroxyl groups are known as diols, while those with two carboxyl groups are called dicarboxylic acids.
Got it. So teacher, what sort of reaction will these compounds undergo?
Well, to learn about that, let's look at an example. For instance, a polyester called polyethylene terephthalate can be formed by reacting terephthalic acid, a dicarboxylic acid, with ethylene glycol, a diol. Let me show you. In this process, water molecules are condensed out. For that, usually a hydroxyl group from the acid part and a hydrogen ion from alcohol combines to form water molecules. When N molecules of each of the monomers are used to form a polyester, the total number of water molecules to be released in the process will be 2N-1 molecules.
Okay. I think I get that. But teacher, I want to know how condensation reactions between monomers actually form such a long chain.
Well, this process can simply be understood in this way. Two monomers first undergo a condensation reaction and form a dimer.
Oh, and the dimer that's formed then continues to extend on either of its sides by reacting with other monomers in a similar way, right?
Absolutely. A long chain of polymers is then formed as more and more molecules are involved. This process can be explained like this.
Okay, but from what you're saying, it seems like there are other ways of chain formation as well, right?
Yep. According to the polymerization theory, there are lots of different ways through which chain elongation occurs. For instance, once the dimers are formed from the monomers, they may either react with the next monomer or dimer to form a trimer or a tetramer respectively. In the same way, when trimers are formed in this process, they may react with the next monomer or dimer or trimer to form a tetramer or pentamer or a hexamer, and so on.
I see. I understand how long chain polymers are formed during the polymerization.
Finding this helpful? we have additional learning resources to offer. For Cambridge IGCSE and AS A-level subjects.
Now we know that polymers are long-chain molecules consisting of a large number of repeating units. The structure of a polymer is simply represented by writing the structure of just the repeating unit with an arbitrary number n like this.
And here n represents the total number of repeating units in that polymer. And this will represent the entire structure of the polymer.
Absolutely.
But teacher, how do we represent the repeat unit for a polymer for any given pair of monomers? Is there a specific method we can use to do that?
Of course. Let me explain it to you with an example. Now, for condensation polymers having two different monomers, we simply pick two adjacent monomers connected by a linkage and enclose them in a bracket. Next, we extend the bonds out from each side, crossing off the bracket by removing the terminal atoms or groups that get eliminated during the condensation. After that, we assign a number n to the right side to represent the total number of such units in the polymer.
Oh, so that's how it's done. I understand now.
Great. Now, moving forward, did you know that the number of repeating units in a polymer is also known as the degree of polymerization of that polymer? Do you know anything about that?
Not exactly. But I guess it represents the chain complexity of polymers, right?
Yep. An increased degree of polymerization along with branching and interchain branching promotes crystallinity in polymers, hence increasing their tensile strength. For example, due to the high degree of polymerization and interchain bonding between cellulose fibers, they have a stable rod-like structure.
Right, okay. I get it now.
Good. Moving on, polyesters can also be formed through the reaction between diol and dioyl chloride instead of dicarboxylic acids. Let's check out this example to explain how it happens.
So in this case, hydrochloric acid or HCl is eliminated instead of water during condensation, right?
Absolutely. And the structural formula of this polymer would look like this.
Right, I get it.
Good. Next up, polyesters can also be prepared using single monomers such as hydroxycarboxylic acids.
That must mean the monomers need to have two different reactive functional groups in the same molecule, right?
Correct. We can take glycolic acid for example. Since it has two active functional groups, it undergoes self-polymerization to form a polymer called polyglycolic acid. Let's take a look.
Wow. So because it has two different functional groups, which include a hydroxyl and a carboxyl group, glycolic acid is capable of undergoing self-condensation to form polyesters.
Exactly. But Divash, did you know that polyglycolic acids are made in many different ways?
Wait, what? There are different ways to obtain the polymer?
Of course. And among these various methods, the most generally practiced methods are the direct polymerization of glycolic acid and the ring opening polymerization of glycolide.
I see. So teacher, which one do people prefer?
Well, when a polymer is made through direct polymerization using a catalyst, it usually forms low molecular weight polymers due to the difficulty of removal of water from the viscous mixture of polymers and water. This means it would require more processing and more energy to remove water to form a high molecular weight polymers, and hence production cost will increase.
I see. That means the ring opening polymerization of glycolide is the best method to produce polyglycolic acids.
Absolutely. The time required for the synthesis of polyglycolic acid through this method is strikingly shortened and the production cost is reduced. Now, please do note that the details of these processes are not required for your syllabus. I just explained it to you just to state your curiosity.
Consider my curiosity sated. Thanks, teacher.
You're welcome.
And by the way, teacher, since polyglycolic acid is made from a single monomer, what does its structural formula look like?
For polyglycolic acid, only a single monomer is included inside the bracket as a repeat unit. Thus, the structural formula of polyglycolic acid looks like this.
Hang on, but this structure doesn't actually show any ester linkage.
That's because two of the same fragments or monomers cannot be put within the bracket. However, if you want to represent the ester linkage better, you can express it alternatively like this.
Oh yeah, you're right, teacher. They're both the same.
Of course. Now, let's move on to something you're more familiar with, polyamides.
Sure. In fact, I'm so familiar with them, I think I can explain this on my own.
Alright, go ahead.
Sure. Polyamides are condensation polymers in which the monomers are linked together by amide functional groups. The general formula of a polyamide looks like this. Here, the CONH group is called the amide functional group or amide linkage. As in polyester, monomers are linked by multiple amide linkages in polyamide.
Fantastic explanation. Now, in molecular biology, the amide linkage is usually referred to as a peptide linkage or peptide bond.
Oh yeah, so that's what they were talking about. So teacher, how do polyamides generally form?
Polyamides are typically formed through the condensation of diamine and dicarboxylic acids. Let me explain this with a real example. Hexamethylene diamine, a diamine and an adipic acid, a dicarboxylic acid, undergo a condensation polymerization in the presence of a catalyst at a high temperature to form a polyamide called nylon.
I noticed that water molecules are condensed out in this process as well, right?
Yup.
And it must also form a long chain in the same way as in polyesters, right?
Exactly. It's done in almost the same way for all condensation polymerizations.
Awesome. So the more monomers that are involved in the condensation reaction, the longer the chain that would form at the end would be, irrespective of the way it occurs.
That's right.
But teacher, why is nylon that's formed in this way written as nylon 6,6 instead of just nylon?
Well, that's simply due to the different types of nylon formed depending on the types of monomers used. As for nylon 6,6, it simply means that the two monomers used in this polymer contain 6 carbon atoms each.
Oh, so that's why. Then teacher, as you've mentioned, there are more ways to prepare nylon, right?
Of course, it can also be prepared by reacting diamine with diol chloride.
Wait, diamine with diol chloride?
Yes, when hexamethylene diamine reacts with adipoyl chloride, a diol chloride, nylon 6,6 is formed.
Want to learn more? We have additional learning resources to offer for Cambridge IGCSE and AS level subjects. Register now for free.